Hello students. So in moving charges and magnetism, also it is a part of electrodynamics. We already discussed about two important concepts. First one is Oersted experiment, which is the basis for the electrodynamics, the development of the branch of electrodynamics, from which it has been found out that electricity and magnetism are two sides of same coin, they are not different. So after that, in the same year, Biot and Savart, they arrived with a mathematical equation for finding out the magnetic field induction or magnetic induction due to a current carrying element that is IDL element, which is a vector, and it is similar to the charge in electrostatics. Okay. Now, so this Biot-Savart's law is universal, means whatever the type of current distribution may be, whatever the type of conductor may be, whatever the shape of conductor may be, to find the magnetic induction at a point, we can use universally that is Biot and Savart's law, no doubt in that. So when we recall about electrostatics, we know there are two laws in electrostatics. One is Coulomb's law. One is the Coulomb's law. So we have Coulomb's law, and another one is Gauss law. One more is Gauss law. So these are two laws in electrostatics. So here Coulomb's law is universal for electrostatics. When the charges are at rest, we want to find what is the electric field or electric force. We are going to use the Coulomb's law. Okay. So Coulomb's law is universal for electrostatics. But however, well, there is some sort of symmetry in the charge distribution. So whatever the charge distribution, irrespective of the charge distribution, we can use Coulomb's law, no doubt in that, it is universal. But however, suppose the charge distribution is having some sort of symmetry. We have seen there are three types of symmetry in the charge distribution. What is the three types? Planar symmetry, we have planar symmetry there. So planar symmetry. Next one is spherical symmetry, and another one is we have cylindrical symmetry. So if the charge distribution is having some sort of symmetry, that is three types, then it becomes very, very convenient and time saving to calculate the electric field due to the symmetric charge distribution. In that case, Gauss law we are using. But Gauss law is not independent. Gauss law can be derived from Coulomb's law. So Gauss law is not a separate law. We can derive that Gauss law from the Coulomb's law. Same comparison now. Same comparison. Here in electrodynamics, we have, see here, this is analogous to, we can say now, Biot-Savart's law. Biot-Savart law. Analogous to Biot-Savart's law. That means what? In electrodynamics, when we want to find the magnetic induction at a point, then we are going to use Biot-Savart's law, irrespective of the distribution of the current carrying element or current carrying conductors. Whatever the shape of current carrying conductor, whether it may be symmetric, non-symmetric, whatever it may be, complex, complicated, anything, we can use Biot-Savart's law to find the magnetic induction or the magnetic field induction at a point due to the current carrying conductor. Okay. But however, if there is some sort of symmetry in the current carrying element or current carrying conductor, If there is some symmetry, then it will become very, very convenient to use this, what do we call, the Ampere's law. So, if the current carrying conductor or the element or the current carrying current element is having some sort of symmetry, then it is very, very convenient to use Ampere's law, just like Gauss law. Just like Gauss law, we can use this Ampere's law. Okay, but there should be some sort of symmetry. But we know practically when we take any current carrying conductors, they are all symmetric only. Example, when you take our electrical wire, you see the transmission line, or you take our domestic wire, they are all cylindrical. So when we want to find the magnetic induction at a point due to a symmetric current carrying element, then it is very, very convenient to use Ampere's law. So now we want to know what is Ampere's law, what is the statement of Ampere's law, and what are the important points when we want to apply Ampere's law, or what are the important characters or points that you have to keep in mind, and after that how to apply this Ampere's law for a solid cylindrical conductor and a hollow cylindrical conductors. So both solid cylindrical conductor, hollow cylindrical conductor, we are going to use the Ampere's law. Okay. So now let us see what is this Ampere's law or Ampere's law statement. First we want to know what is that Ampere's law statement. So Ampere's law statement. We want to know first what is the Ampere's law statement here. Okay. So now let us see what is the statement of the Ampere's law. So first of all, here when we want to apply Ampere's law, means we want to know the statement of Ampere's law, we are going to take some imaginary loop. Maybe real, maybe imaginary. Most of the case it is imaginary loop, that is closed surface. Imaginary loop that encloses the current carrying conductors. Right. We know when a conductor is carrying current, means here the current can be coming out of the plane or going into the plane. Like magnetic field, if the current is coming out of the plane, means example board is a plane. Suppose when a current is coming, a conductor is there carrying the current, that current is flowing upwards, that is coming out of the board, and it is going down, that means current is going into the plane. So now suppose, for example, there are two conductors here, say there are two conductors, minimum. For example, I am taking two conductors. So there are two conductors carrying current. So this is one conductor, and say this is another conductor. Two conductors, any number we can take. But for example, to know the statement, I am taking only two conductors now. In this, now see here, one conductor is carrying current into the plane. It is carrying current into the plane. Okay, into the plane. Means it is going into the board. Next, another one, it is coming out of the plane. Another conductor is carrying current out of the plane. So second one is out of the plane. So these two conductors. Right. This is another conductor. Now we want to find the magnetic induction at a point in the space due to these two current carrying conductors. Then what we are going to do is, we are going to imagine that these two current carrying conductors are enclosed by a closed surface, an arbitrary